Hello, dear students. We are start our lesson by interchangeability, standardization, and technical measurements. Today's laboratory work number 3. The task number 1, calculation of limit deviations, limit dimensions of parts of a cylindrical connection, and the choice of a standard fit. First, what we need to do, it's for a cylindrical joint with a nominal fit, big diameter, big D is equal 63 millimeters, and given values of the smallest and largest clearances or interferences in micrometers, big N minimum, it's minimum interference is equal 36 micrometers, and maximum, its maximum interference is equal 85 micrometers. It is necessary. Select according to this to ISO 286-2002 the numerical value of the tolerances for the processing of the shaft and hole, determine the IT grades and fundamental deviations. For the formation of a fit in the whole system, determine the numerical values of the upper and lower deviations of the hole and the shaft. Build a scheme of the location of the tolerance fields of the hole and the shaft. Apply the main designations and numerical values of all connection parameters. Make a schematic drawing of the connection of the hole with the shaft, separately the hole and the shaft. Indicate the dimensions of the connection, hole and shaft in the drawing in different ways. Select the numerical values of the roughness of the parameter RA depending on the IT grades of accuracy, and indicate on the sketches of the shaft and the hole. Build a general scheme of tolerance fields for parts, limiting working and control gauges. Calculate the dimensions of the gauges. Make a sketch drawing of working gauges plugs and gauges brackets with marking and designation of execute dimensions. For a cylindrical joint with a nominal fit, big D is equal 63 millimeters, and given values of the smallest and largest clearances or interferences, and minimum is equal 36 micrometers, and maximum is equal 85 micrometers, select according to ISO or this to 286-2002 the numerical value of the tolerances for the processing of the shaft and hole. Determine the type of fit. If the limit values of the clearances are set, then the fit with the clearance. If the limit values of the interferences are set, then the fit with interference. If the maximum interference and the maximum clearance are set, then fit is transitional. So what we have? We have maximum and minimum interferences. So we have the limit values of the we have the limit values of the interferences. Then we have the fit with interference. So since the limit values of the interferences are set, the fit with interference. Tolerance of interference fit is equal maximum interference minus minimum interference. And we can calculate it 0.085 minus 0.036 in millimeters, and we have 0.049 millimeters. At the first stage of the calculation, we accept the tolerances of the hole and the shaft as equal as it corresponding to the same IT grade. Big TD is equal small TD is equal tolerance field divided by 2. Tolerance field is equal 49. Divided by 2, we have 24.5 micrometers. The nearest standard values of shaft and hole tolerances it's IT grade 6. The correctness of the accepted tolerances is checked by compliance with the condition. Tolerance field of the feet is equal tolerance field of the shaft plus tolerance field of the hole. Tolerance field of the shaft 19 micrometers, tolerance of the hole 19 micrometers, tolerance field of the shaft 19 micrometers too. So 19 plus 19, we have 38 micrometers. Behind the task is 94 micrometers. 94 micrometers is not equal to 38 micrometers. So, as equal is not reached, we accept the IT grade of the hole for one lower than shaft. The closest standard values correspond to grades IT6 and IT7. The tolerance values of shaft TD small is equal 19 micrometers. It's for IT6. And for the whole big TD, it will be equal 30 micrometers. It's for IT7. Once again, we check the correctness of the equal. And the sum of the tolerance field of the shaft and of the hole, 19 plus 30, we will have 49, and we have that in the task 49 micrometers. So the equal is reached. Determine the numerical values of the upper and lower deviation of the hole and the shaft for the formation of a fit in the shaft system. The fundamental deviation of the shaft in the shaft system, small es, is equal 0. To determine the main deviation of the hole, build a graphical representation of the fit in the following sequence. Draw a zero line which conventionally indicates the nominal diameter of the connection. nominal diameter of the connection is equal 63 millimeters. Construct the tolerance field of the shaft H6 and put its maximum deviations from the zero line small es is equal 0, small e is equal minus 19 micrometers. Build the tolerance field of the hole below the tolerance field of the shaft based on the specified values of the parameters of the feet with interference. Determine the maximum deviation of the hole. Upper limit deviation of the hole is equal lower limit deviation of the shaft minus minimum interference. Small e is equal minus 19 and minimum is equal 36. So minus 19 minus 36, we will have minus 55 micrometers. Lower limit deviation of the hole is equal upper limit deviation of the shaft minus maximum interference in the feet. So upper limit deviation of the shaft is equal 0. And maximum is equal 85, 0 minus 85, and we have minus 85 micrometers. Therefore, the numerical value of the fundamental deviation of the hole is minus 55 micrometers. For diameter, nominal diameter 63 millimeters, the maximum deviation of the hole, big E, is equal minus 55 micrometers, and big E is lower limit deviation of the hole is equal minus 85 micrometers. In the 7th IT grade correspond to the tolerance field IT7. The standard fit T7H6 chosen by us provides the set values for functional interferences and maximum 85 micrometers and n minimum 36 micrometers. Determine the maximum dimensions of the hole and the shaft. The maximum size of the hole. Nominal diameter of the hole plus upper limit deviation of the hole, and we have 63 plus minus 0.055 in millimeters. And we have 62.945 millimeters. The minimum size of the hole. It's equal nominal diameter plus lower limit deviation of the hole. Nominal diameter 63 plus minus 0.085, and we have 62.915 millimeters. Maximum shaft dimensions. Maximum diameter of the shaft, it will be equal nominal diameter plus upper limit deviation of the shaft. Nominal diameter of the shaft 63 millimeters plus 0, and we have 63 millimeters of the small d maximum is equal 63 millimeters. Minimum diameter of the shaft is equal nominal diameter of the shaft plus lower limit deviation of the shaft. 63 plus minus 0.019, and we have 62.981 millimeters. Build a scheme of the location of the tolerance fields of the hole and the shaft, and apply to it the basic symbols and numerical values of all connection parameters. The scheme of the tolerance field on the hole, of the hole, and of the shaft. So we have zero line, above zero plus, above zero line we have plus, under zero line we have minus. Tolerance field of the shaft, H6. Upper limit deviation of the shaft, it's equal 0. Lower limit deviation is equal minus 19 micrometers. Tolerance field of the hole, T7. Upper limit deviation of the hole, big ES, is equal minus 55 micrometers. Lower limit deviation of the hole is minus 85 micrometers. Tolerance field of the hole, big TD, is equal 30 micrometers. Big EE minus big ES. Minus 85 minus minus 55, we will have no. Big ES minus big EE. Minus 55 minus 85, we will have 30 micrometers. Big TD will be equal 30 micrometers. And we have maximum diameter of the hole and minimum diameter of the hole. Maximum diameter of the shaft, and minimum diameter of the shaft. Maximum interference of the feet and minimum interference of the feet. This is the scheme of the tolerance field of the hole and the shaft. Write down to your notes this scheme as an example. You have the time, do it. And we are continue. Perform a scheme drawing the connection of the hole and the shaft separately, the hole and the shaft. Indicate the dimensions of the connection, hole and shaft in the drawing in different ways. So you can see in the scheme, schematic drawing of the connection and schematic drawing of the shaft and of the hole. On the drawing of the shaft, we can see three variants of dimensions. We have nominal diameter 63 and tolerance field H6. H is fundamental deviation of the shaft, 6 IT grade of the shaft, of the tolerance field of the shaft. Second variant of designation of dimension of the shaft, we have a nominal diameter and deviations, upper limit deviation and lower limit deviation of the shaft. And the third variant of dimensions on the drawing, we have what we have. We have nominal diameter 63 millimeters and tolerance field and upper and lower deviations, both of these parameters. The same three variants we can see on the scheme of the hole. We can see hole and first variant of the dimension. We have diameter 63, it's nominal diameter of the hole, and tolerance field of the hole. Fundamental deviation T, IT grade 7. Second variant of the dimension of the hole, it's nominal diameter of the hole, and upper limit deviation of the hole and lower limit deviation of the hole. Minus 0.055, it's upper limit deviation of the hole, and minus 0.085, it's lower limit deviation of the hole. And the both variants of these parameters together, we have nominal diameter, we have tolerance field of the hole, and we have deviations, upper limit deviation and lower limit deviations of the hole. And what we can see for connection of the shaft with the hole. For connections, for connection of the shaft with the hole, we need to write nominal diameter of the connection, again diameter 63, and line, we have line, above the line tolerance field of the hole, under the line tolerance field of the shaft. We have T7 for the hole and we have H6 for the shaft. So above the line we see T7, big T, and under the line H6, small h, small letters for the shaft. Second variant of designation of the diameter, only deviations we have. Nominal diameter 63, and above the line, parameters of the hole, upper limit deviation of the hole and lower limit deviation of the hole. Under the line, upper limit deviation and lower limit deviation of the shaft. upper limit deviation of the shaft 0, lower limit deviation of the shaft minus 0.019. And third variant of the diameter, nominal diameter, tolerance fields of the hole and of the shaft, and deviations of the hole and of the shaft. Above the line parameters for the hole, under the line parameters for the shaft. Please write down to your notes all these schemes, all this drawing. You have the time. Do it, please. We built a general scheme of tolerance field for parts, limiting working and control gauges. The scheme of the tolerance fields of parts, gauges, and contour gauges for feet, diameter 63, T7, H6. We have tolerance field of the hole, T7, tolerance field of the shaft, and tolerance fields of the working gauges. Go and not go, it's go, and it's no go. And control gauges, control gauges, no go, control gauges, go. And working gauge, it's for shaft, no, for hole, no go side, and go side, it's go side. So you can see the tolerance fields of these gauges. Write down to your notes this scheme of the tolerance fields of parts, gauges, and contour gauges for feet diameter 63, T7, H6. T7 it's tolerance field of the hole, H6 tolerance field of the shaft. Tolerances for the manufacture of snap gauges, plug gauges, and contour gauges were of go gauges, and y offset of the middle of the tolerance field of go gauges are found in the table of standards based on the nominal size of the connection, big D and IT grades of the hole and shaft. Because D is less than 180 millimeters, the parameters alpha and alpha suffix 1 are 0. For shaft, big D is equal 63 millimeters of IT grade 6 snap gauges parameters, H suffix 1 is equal 5 micrometers, Z suffix 1 is equal 4 micrometers, Y suffix 1 is equal 3 micrometers, alpha suffix 1 is equal 0, and the counter gauge parameters H suffix P is equal 2 micrometers. For hole, nominal diameter 63 millimeters, IT grade 7, plug gauge parameters H is equal 5 micrometers, Z is equal 4 micrometers, Y is equal 3 micrometers, alpha is equal 0. According to the constructed scheme, we calculate the limiting and worn sizes of gauges and contour gauges, and we enter results in table 1.1. Write down to your notes these formulas to determine the dimensions of plug gauges and limit dimensions of the snap gauge. And we are continue limit sizes of contour gauges. Calculate the executive dimensions of the gauges. The executive size of the snap gauge, go and no-go, is its smallest limit size with a positive deviation. Plug gauge, go and no-go, the largest limit size with a negative deviation. Thus, the deviations are put in the body of the gauge, which provides a maximum of metal for manufacture. Therefore, the executive dimensions of the snap gauge go diameter 62.9935, upper limit deviation 0 plus 0.005, lower limit deviation 0. No-go, diameter 62.9785, upper limit deviation plus 0.005, lower limit deviation 0. And the executive dimension of the plug gauge, go diameter 62.9215, upper limit deviation 0, lower limit deviation minus 0.005. And no-go side, nominal diameter 62.9475, upper limit deviation 0, lower limit deviation minus 0.005. So write down to your notes these formulas and executive dimensions of the snap gauge and of the plug gauge. According to the constructed scheme, we calculate the limiting and worn sizes of gauges and contour gauges, and we enter results to table 1.1. Write down to note this table with all parameters. It's part of the table for the hole and for the shaft. We make a sketch drawing of working plug gauges and snap gauges with marking and designation of executive dimensions. The principle of gauge marking is that the gauge is marked with information that relates only to the controlled part. The snap gauge indicates the symbol of the shaft size, as well as go and no-go shaft boundaries. That is, the upper deviation is 0 for go and the lower deviation is 0.19 for no-go. The plug gauge size indicates the hole size, diameter 63 T7, as well as the upper deviation minus 0.055 for no-go and lower minus 0.085 for go side. So write down to your notes, figure 1.4, executive dimensions and gauge marking. After that, you should take your variant of this task and repeat all calculations with all scheme for your variant. It's laboratory work number 3. So do it now. Please choose your variant and repeat this calculation using your initial data in your variant. So our lesson is finished. See you next week. Be careful and goodbye. Have a nice day.